Hi everyone, in this video, our team ChemTech Titans will be presenting our integrated design project where we have designed a reactor separator system to meet the annual demand for medical grade nitric oxide. Before we dive into the details, let's start by introducing ourselves. Hi, my name is Fakhrul bin Sabudin with student ID 22001466.
Hi, I'm Kasturi Puspanathan with the ID number 22008056.
Hi, my name is Ying with student ID 22007922.
Hi, my name is Ariana, binti Abdul Razak, and my student ID is 22003556.
I am Balqis Adlena binti Khabirullah, and my student ID is 22006780.
For our process, we have designed a process flow design of a reactor separator system symmetry. We begin with the mixer, where ammonia and oxygen are mixed together. The ammonia feed is 3500 kmol per hour and the oxygen feed is 4500 kmol per hour. At this stage, the gases are at ambient conditions with a temperature of 25 degrees Celsius and a pressure of approximately 101 kPa. Once mixed, the gas stream enters the compressor where the pressure is increased to 1000 kPa. This compression step is crucial to enhance reaction efficiency in the next stage. After compression, the gas mixture is heated in the heater to 950 degrees Celsius. This high temperature is necessary to facilitate the oxidation reaction that occurs in the packed bed reactor. Inside the reactor, ammonia reacts with oxygen in complex reactions with the aid of platinum rhodium gauze catalyst to produce nitric oxide, nitrogen dioxide, and water as overall products. The high temperature and pressure ensure a higher conversion rate of ammonia into desired product. Following the reaction, the gas mixture enters the cooler where it is cooled down to 250 degrees Celsius before proceeding to the separation stage. Cooling is an important step as it improves the efficiency of the adsorption process. Finally, the gas enters the adsorber, which is used to separate the desired nitric oxide from other byproducts. The process results in two output streams, which is S6, which contains ammonia, oxygen, and water, and also nitrogen dioxide, and S7, which is primarily composed of 96% of nitric oxide, our final product. This concludes the overall process from raw material preparation to final product separation.
I will introduce our case study on designing an optimized reactor system that maximizes NO yield while minimizing impurities, ensuring it meets strict medical grade standards. Nitric oxide is essential in treating pulmonary hypertension and improving oxygenation in neonatal care. It is primarily produced through the catalytic oxidation of ammonia, yielding NO and water vapor. However, such reactions can lead to the formation of undesirable byproducts such as nitrogen dioxide and unreacted ammonia, which must be carefully controlled. To address this, our project focuses on the design, optimization, and purification of a reactor system that maximizes NO yield while minimizing byproduct formation. By integrating reaction engineering principles and separation techniques, we aim to produce high purity NO that meets strict medical grade standards.
Now, let's look at the introduction and objective of separation process 2. In the ammonia oxidation process, impurities such as unreacted NH3, NO2, O2, and H2O must be removed to obtain high purity of nitric oxide. The key objective includes selecting a highly selective adsorbent that effectively captures these impurities, designing an optimized adsorption column with suitable material, diameter, and height, and incorporating adsorption isotherm to analyze the equilibrium capacity.
Now, let's begin with the primary reaction, which is oxidation of ammonia using oxygen to form nitric oxide. So this reaction occurs over a platinum rhodium catalyst at high temperature 950 degrees Celsius. So the reaction is first order, meaning its rate directly proportional to the concentration of ammonia, with an activation energy of 115 kJ per mole. It requires significant thermal energy to proceed. The process is exothermic, so careful control is necessary to prevent side reaction and ensure efficiency. The reaction is carried out at 10 bar pressure to maintain the desired conversion efficiency. Once nitric oxide is formed, it undergoes further oxidation to nitrogen dioxide through the reaction. Unlike ammonia oxidation, this reaction occurs at lower temperature and does not require a catalyst. The activation energy is much more lower, 33 kJ per mole, making this step significantly faster under normal atmospheric conditions. This reaction is particularly important for the production of nitric acid, which has widespread industrial application. To maximize nitric oxide production efficiency, it's essential to use the optimal catalytic system and reaction condition. The ideal reaction condition for efficient nitric oxide production include maintaining a temperature between 850 to 950 degrees Celsius to maximize yield while preventing excessive byproduct formation. The pressure should be kept between 4 to 10 bar, striking a balance between enhancing reaction rate and minimizing equipment costs. An ammonia to oxygen ratio of 1 to 10 ensure complete ammonia oxidation while preventing catalyst deactivation. Additionally, a resident time of 1 to 10 milliseconds is crucial for maximizing nitric oxide selectivity while minimizing the formation of nitrogen dioxide. Product catalyst regeneration strategies such as burning off surface deposit can extend the catalyst lifespan and maintain efficiency. From an economic standpoint, although platinum radium gauze has a high upfront cost, it is recyclable, making a viable long-term investment. Operating at moderate pressure helps reduce overall costs by avoiding expensive high-pressure equipment. This system provides over 95% conversion efficiency with minimal byproduct formation, leading to lower purification costs in downstream processing. By optimizing this factor, this catalytic system ensures high nitric oxide yield, processing efficiency, and economic viability, making it the best choice for industry-scale production.
Next, I will explain about reactor sizing and reactor type used for this process. Volume calculated based on the Levin spill plot for CSTR is 20.39 m3, and for PBR or PFR is 3.59 m3. PFR or PBR is more preferred than CSTR because it has low volume, and according to the expansion factor, this means that for every mole of NH3 reacted, the total number of moles in the system is increased by 10.93%, and the weight of catalyst obtained is 7,336.3 kg required in the reactor to maintain a steady reaction rate and achieve the conversion of 63.1% of ammonia into nitric oxide. For the reactor type, pipette reactor is the most suitable choice for industrial-scale nitric oxide production from ammonia due to its high efficiency, selectivity, and thermal control. Using a platinum-rhodium gauze catalyst, the PBR provides a stable structure that enhances conversion efficiency while minimizing unwanted byproducts like NO2 and N2O. Compared to belt flow reactor, the PBR ensures better heat management and catalyst longevity, making it a more cost-effective and sustainable option. Its continuous operation, low maintenance, and recyclability of the catalyst further reinforce this role as the preferred reactor for ammonia oxidation in nitric oxide production.
Firstly, before developing the adsorption column, we have to determine the concentration of each impurity in the ammonia oxidation process. We first calculated the total gas flow rate entering the adsorbent, and we got 83.56 m3 per hour. Then, we determined the individual flow rate of all the 5 species involved. Finally, we found the concentration of each species by dividing its flow rate by the overall flow rate. These values help in designing the adsorption column to effectively remove the impurities and achieve 99.9% pure nitric oxide. The purification system employs a fixed bed adsorption column with zeolite 13X selected for its high cation exchange capacity, large surface area, and strong affinity for polar and oxygenated species. The process begins with a condenser that cools the gas mixture, causing water vapor to condense. A two-phase separator then removes the condensed water, reducing moisture content before adsorption. The gas then flows through the two-layer zeolite 13X adsorption column. The first layer primarily removes the residual H2O and unreacted NH3, as zeolite 13X efficiently adsorbs ammonia due to its strong electrostatic interaction with the polar molecules. The second layer captures the remaining O2 and NO2. Zeolite 13X adsorbs O2 through the van der Waals interactions, and NO2, being the highly polar, interacts strongly with the charged surface of zeolite 13X. This setup ensures that only high purity of NO exit the system.
In 3.3, we need to identify the type of adsorbent used, which is zeolite 13X. The isotherm model we have chosen for this absorption column is Langmuir isotherm. Image above shown is a model of the Langmuir isotherm, which is equation before and after linearization is being presented. The reason why we choose Langmuir isotherm is because we assume a monolayer adsorption, meaning that adsorption occurs only in the homogeneous surface with a fixed number of active sites, holding only one molecule of adsorbate. This aligns well with our zeolite 13X adsorbate. Next, constant binding energy is being assumed. Each active site have same energy and do not interact with each other, forming a uniform system. Langmuir isotherm is also suitable to be used for reversible absorption that eventually reaches equilibrium, which describes the relationship of impurities and zeolite 13X. Lastly, the high selectivity and strong interaction between zeolite 13X and impurities. By applying Langmuir models, the absorption capacity and efficiency can be effectively determined and aid in the separation process. Because of the nature of gas, the adsorbent flow in an outflow configuration due to the gas having a lower density than air. Besides, adsorption column is also made up of stainless steel. This is because of its mechanical properties, chemical stability, corrosion resistance that make it ideal to handle reactive gas like nitric oxide, and its versatility. Other than that, determining the mass transfer zone is also important in the design of adsorption column. The length of anti-zip could be identified in the equation in red to allow us to optimize the column performance and assuring the efficient utilization of adsorbent and prevent premature breakthrough. In our IDP, we have made some assumptions using McCrafe journal as reference. We assume that anti-Z length is 50 cm with a column diameter of 2 cm and a column height of 76 cm. In laboratory scale, by upscaling with a ratio of 1 to 10, the anti-Z length is 500 cm and column height of 760 cm. In order to achieve 99.9 purification efficiency, the regenerating of zeolite 13X is capable of recovering adsorbate molecule and allowing adsorbent reuse through detachment of adsorbate form saturated bed. The regeneration is typically done through chemical purging desorption, thermal swing desorption, and pressure swing desorption. By continuous regeneration, zeolite 13X can be reused multiple times without significant loss of efficiency. Therefore, this method is very cost-effective and sustainable in a long-term planning because less adsorbent is needed to be purchased and go to waste, while using this method to achieve 99.9% of purity efficiency of nitric oxide.
As a conclusion, we have designed a reactor separator system for medical-grade nitric oxide production from ammonia oxidation. A platinum rhodium catalyst and packed bed reactor ensure efficiency and high selectivity. To achieve 99.9% purity, an adsorption-based system remove NO2 and NH3 with optimized separation and regeneration for cost-effectiveness. This design creating an efficient, scalable, and sustainable system for industrial application. That's all from us. Thank you.